Okay, the tunneling of Cooper pairs, we are concerned more about that here. So, the discovery of macroscopic quantum mechanical tunneling and energy quantization in the electric circuit. So this circuit, as I showed, mentioned that in replacing the L with a different element, which is a junction like that, superconductor, insulator, superconductor. So you have to understand a little better now. So what does the superconductor do? Superconductor is zero resistance, right? So that means if I have a superconducting material ring like that, superconducting material, and if I take a magnet and hold it like this and take it out, what will happen? The magnetic field changes will induce a current, right? And this current can remain forever because there is no loss. Energy loss is I square R. Since R is 0, there is no loss. So it will remain forever. So energy dissipation is not there in this case. So you use a material like that, like replace this copper wire by two pieces of superconductor, and you have an insulator here. Now if you connect it here, even without a battery, you will get a current. That's different. Ordinary, through the copper wire, you have to apply a voltage. Then you got a current. But here, without applying anything, you can get a current. That was the theoretical contribution also to Brian Josephson. And this is other interesting things happen. So this is the structure of this semiconductor, superconductor, insulator, superconductor. But if you just close this circuit without any voltage, you get a current. But if you apply a voltage, without battery. But if you apply battery, what happens? This phi changes with time. So if you change phi with time, sinusoidally current will vary, right? So you get an alternating current. So without battery, you get a DC current. Without applying a voltage, you can get an AC current, alternating. All these phenomena are different. Without a superconductor, you don't get this. Right? So this is called the DC Josephson effect and AC Josephson effect. But based on which this Nobel Prize was given. You notice one thing that here, energy level quantization in the 0 volt state of a current biased Josephson junction. Right? And this is measurement of macroscopic quantum tunneling out of the 0 bias state on a current biased Josephson junction. Everything is Josephson junction is the central electric element. That's what is necessary for this demonstration. So now I go back to the same circuit. Now if you want to make a diagram for electric equivalent circuit, so this is my Josephson junction here. And since these are two pieces of metal, which are superconductor, but this is an insulator. An insulator between two pieces of metal, it's a capacitor, right? So there is a parallel effective capacitor here, parallel. But since this is an insulator, this may have some resistance. So I put that parallel resistance here also. Now I pass a current through this. So this is my equivalent circuit. So this current biased means I keep this current fixed, constant. Then this current will be divided into 3 channels, right? So I can write my equation current equal to 3 components of currents on the right side, right? So this is this left side, which is this current I am passing. Q equal to CV, right? C, capacitance times voltage. So dQ by dt is the current, right? So voltage derivative we have to take. So V dot. So this is the current through the capacitor, this is the current through the resistor, and this is the current through the Josephson junction. That was given by the first Josephson equation. Right? So now you can actually rewrite this in this form. What is the H cross over 2E we have multiplied on both sides. And then we have this. So now this is an equation of phase, this phi. Right? So what is the dynamics of this phase? Can you relate it to whatever you have learned in undergraduate physics? Let's see. So, can you see what is this? It's a damped driven harmonic oscillator, right? Damped driven harmonic oscillator is nothing much, not much different. So this is a harmonic oscillator, right? And if it is, of course, it will not run forever. It will be damped. It's already damped. But say if I take a tuning fork I attach it somewhere here so that we will keep frequency, right, with that frequency. That's the forcing. So damped forced harmonic oscillator. So that we got the same equation as that. We have to solve that one. So we already have learned the solution in undergraduate physics. So let's look at it. That is the same equation. That's a little rearrangement here with this multiplication factor seen. But here it is written as del u. U is the potential, del u by del phi. But you said if u is this, if you take this derivative, you will get the same thing. So this is the potential for that. So now we call this external, that current that I have given, I call it a bias current. Take my bias current is 0 here, so this term is 0. So my potential has a cosine function, which is this one, right? But now if I add this, if I have this bias current, then depending on that, this is a constant slope, it will be added. So that means if I increase this bias, I get this potential changed like this. It's called a washboard potential. The dhobis usually use something like corrugated board and then they do that. That's the washboard potential. And that is very important. So we are looking at now, this system now is the ground state. Say I don't have this term, so it is this term, right? So this is the minimum of the potential. Like harmonic oscillator, it oscillates. This will phase also will oscillate within that. We call it a phase particle. Now we can tune these different conditions and study them in more details. So if it is like this potential, but if it is like this, you see that from the depth to the hill, barrier is smaller, right? Potential barrier. Here it is 0. That here this particle can escape easily. So within this, we are going to study what happens in details. Say for example, we have the middle case, something like this, right? Now the phase particle which is there, it has two options. If it has enough energy, it can jump over this barrier, go to the other side. Or if it doesn't, it has another possibility. If it is quantum, it can tunnel through this barrier, right? So that was the first experiment that this Nobel laureates have shown and demonstrated, that it really tunnels. If it tunnels, then it is a quantum system. So how did they do that? So this is another thing that let me go through this. If it is a classical particle, it's a big one, it has no chance of tunneling, as I mentioned at the beginning. But if it is a quantum particle, it's associated with this uncertainty principle. Delta x times delta p is of the order of that. So that means it is not localized at one position. It has a position spread, it has a momentum spread. What does it mean? It is represented by wave packet. And once it is represented by wave packet, the wave can tunnel through potential barriers, right? So either you have the option of proving that it is a wave packet, or the other option is you show that they are really tunneling. Then you can say that it is quantum. So this picture again confirms that if it is a classical particle, it will be able to bounce back. But if it is a quantum particle, it has a wave, and that wave has certain probability of passing through that. Right? So these are the options. Like here is if it is wave, the wave function can actually have some probability of going through the other side. So this was the experiment that they have done, that they're detecting what is coming out from here. And this expression tells you that, think of a classical particle under a potential difference, then this is the exponential minus delta u divided by kBt. If t is infinity, this term is 0, right? E to the power 0 equal to 1. So then, forget about the prefactor, which is a constant in this case. So you get these values, but if you now keep on changing t, this gamma will keep on changing, right? And it will follow, if you make a log-log plot, it will follow a linear, because this is exponential in there, this curve. And they measured the escape rate at different temperatures, and they found this follows this classical prediction. But below this temperature, when they go, they see that this doesn't follow the classical prediction of that. But still they are coming out, right? The only option is now then, they are coming out by tunneling. Classically, the classical behavior would have said it almost goes to 0, the tunneling. the escape probability. Now below this temperature, since they can still go, they can come through, that means they are tunneling. It's a quantum tunneling phenomenon. And this another theoretical physicist, Anthony Leggett, predicted this phenomenon at near T equal to 0. So this is near T equal to 0 actually, this is below 40 millikelvin. And he was also Nobel laureate, Tony Leggett, but this prediction was also verified here. Second thing is the energy quantization, and here I have put this energy quantization for the atom, which is hydrogen atom, right? Now imagine that my phase particle here is trapped somewhere here. So if it has to tunnel, then it has to go through this barrier, right? High barrier. So its tunnel rate would be small. But if it is here, then it has to go through a thin barrier. So its tunneling rate would be much higher, right? Like the copper example I've given, if the gap is small, you get more current. If the gap is larger, you get less and less current. Similar things should happen. So what they have done, these Nobel laureates, they have started with a system and then they tried to excite these from one level to the upper level. Now you see that if I apply any energy, here if I apply a photon that has this much of energy, it cannot cause this transition, right? So if I here tune a fixed energy that matches with this energy difference, then they can excite to the next level. And that's exactly what they have done. So in this case, you start with this, for example. If I have this one, this barrier is small, this barrier is smaller, this is 0. So we remain from here to somewhere here, right? Then what we are doing is every time we are reducing the depth of this tunneling barrier, right? And so this is what this present is. Even depending on the depth of this, the energy levels will also be like that, right? Now, say for example, if I apply a microwave pulse from here, this is a microwave with a frequency you have chosen, 2 gigahertz. So we know the energy, H nu is the energy, right? We know the energy. Now, for example, in this scenario where IB1, say IB value we have chosen like 1, these energy levels actually match with that. But for this case, when the oil is shallower, then this will not match, it's a lower level, this will match. When it is even shallower, then this level here will match, not the other ones. So what is they have to show? They have to shine this in this case, and they show that when they have excited here, you have tunneling, more tunneling. In this case, they will have more tunneling. In between, they will not have matching. For any other in-between current, the oil will not be right to give a matching energy difference. So that's what they have done. So as you see here, these three cases, by changing the IB, this is current I. So IB1, IB2, IB3, that's what I've shown. And these places, they have this enhanced escape of this particle. So that shows that energy levels are indeed quantized. Otherwise, they won't call this specific excitation with these photons, 2 gigahertz photons. So quantum tunneling as well as energy quantization. These are the two things. Quantum behavior, they are shown for this electric circuit that contains a reception junction. So this circuit now shows energy quantization and quantum tunneling. And that is why these people got the Nobel Prize by demonstrating that. Now let's look at it. Since this is a quantum system, this circuit, right, and it is behaving quantum mechanically. So it is like a large atom. Atoms are quantum, right? So this is analogous to an alpha decay in which a heavy atom emits an alpha particle, right? So let's see what happens. This cartoon, that's how the alpha particle is emitted. But these alpha particles would not have been emitted because this is when they are produced, they get some energy as this. But they have a potential barrier there, which is like that. Unless they can cross this potential barrier, the alpha particle will be trapped inside. It cannot come. But it's because of this quantum tunneling through this barrier, that's how the alpha particle can come out. So by this quantum circuit now is a big one, it's macroscopic actually. It is behaving like a nucleus that's emitting an alpha particle. Such a fully quantum behavior that it is displaying. Now let me give you a picture of that. Three types of tunneling I just explained. One is that tunneling in a metal, right? Electron tunneling. Second one I showed the tunneling in a gap with superconductor. That's the Cooper pair tunneling. The last one that I showed that happens near absolute zero. Still, it's not a single Cooper pair tunneling. It's the whole system is now a single quantum system. So its flow is like the flow of a river without resistance as a whole. That's the domain, third domain that it represents. Now, these electric circuits also show other important quantum properties such as superposition and entanglement. These quantum concepts were not there earlier. So these properties also are shown by these quantum circuits, which is apparently macroscopic. And the quantum science associated with the 2005 25 Nobel Prize has already been produced a breakthrough quantum technology, namely superconducting quantum computer. One of the three Nobel laureates, John Martinez, he was also involved in making the Google's first quantum computer, superconducting quantum computer. Now, what are the differences between classical and quantum? This side is classical. Its information is stored as a bit, 0 or 1. It's like a transistor switching off or on. It's a two. But it's a quantum part is that it is stored, information is stored not as 0 or 1. It's a 0 and 1. It's a superposition state between 0 and 1. So it is represented by a superposition of two quantum states. So that's the quantum beat is represented by that. It's a new quantum state, which is a superposition of two quantum states. So now, let's go back between the difference between the ordinary LC circuit and the LC circuit that we came across just now. So in ordinary LC circuit, you can, by choosing proper values of L and C, you can choose your omega, right? So you can choose the discrete energy level. That would be quantum. But it's actually a harmonic oscillator, right? It's an harmonic oscillator. But the problem is, if I want to build a qubit or a superconducting quantum computer, with this, we have a problem because we have to interact with a microwave photons. It's a fixed energy. Now you see that here the difference between 0 and 1 state is the same as the difference between 1 and 2. But I want to work with just two states here. So accidentally I'll just excite the other one also. That everything would be wrong. So what I need is an asymmetric. This is symmetric, this is asymmetric. This is still harmonic oscillator but asymmetric. So when it is asymmetric, then the energy levels are not equally separated. So this is larger than this one, than this one. Now if I work with a photon that has this energy, then I don't accidentally put there. So that's why you need this asymmetric harmonic potential. And that is provided by this new L, that is the Josephson junction, which I have just shown. As I shown, that's a linear, the expression I showed, V equal to L times di over dt. That was L was a function of phi. So that means this is not a linear, it's a non-linear. And that's what you get from this anharmonic potential. And that is what is important for developing superconducting quantum computer. So you have this case and you interact with a microwave photon. The energy is equivalent to the energy difference between these two. Now this is, many of you have seen probably 2019. That was the Google built the superconducting quantum computer. Actually John Martinez, one of the Nobel laureates, he was the leader of this. And they produced a 53 qubit quantum computer. And they showed that they could carry out a calculation in 200 seconds. And then they showed that, estimated that the best classical computers would take 10,000 years to complete. What is the best classical computer? Something like this. This is no National Lab. 100 billion bits. So this is a small baby, right? This is 54 qubits, and that's 100 billion bits. Still it is so powerful. Right? And they improved this further a few years later, this is last year in December. Then the quantum chip with 105 qubits instead of 5, and they performed a standard benchmark computation in under 5 minutes that would take one of today's fastest computers 10 septillion years, 10 to the power 25 years. What's the age of the universe? 10 to the power 10, of the order of 14 billion years. It's of the order of 10 to the power 10. 10 to the power 25 years, can you imagine? It's far longer than the age of the universe. So that means it's something that is impossible by the most powerful classical computer can be achieved with even a small quantum computer. So there are huge applications of quantum computers, just to brush things, medicine and materials, banking, financial services, artificial intelligence, communications, cryptography, logistics and supply chain, military defense. Cryptography is something that when you get a message from the bank, sometimes you notice that this is 128-bit encrypted. So that you and the bank, they know it. Nobody else knows, nobody else can break. But these communications can be broken, someone else can easily see it. But if you use a quantum cryptography, then nobody will be able to break it. That's sure communication. There are many. So let's move ahead. The development of superconducting quantum computer in our lab. This is called the dilution refrigerator. As I said, that quantum phenomenon that is close to absolute zero. So we have about 10 millikelvin here. 10 millikelvin is 0.01 degree above absolute zero. Absolute zero is minus 273.15 degree, and this is minus 273.14 degree. And that sort of temperature first create. And then we integrated all the electronics inside this gradually. And then this is inside this one is our 1 qubit, not 53 or 105, just 1 qubit. And that's housed in this. And the cylinder that you see is very sensitive to the magnetic field of the Earth. So you have to shield that. And inside this box you have a cavity like that, and through that we inject the microwave. And at the center of that is actually the qubit. It's magnified, this qubit. It's a Josephson junction is here, and it has its own parallel capacitors, and then it's an additional capacitor. And this is actually the Josephson junction. It's like an aluminum finger like that. It's oxidized here, which is an insulator, and then another aluminum finger. So aluminum becomes superconductor at that low temperature. It's superconductor, insulator, superconductor. So that's at the heart of this qubit. So this is the equivalent circuit of the Josephson junction as I showed. And this is the additional, this is LC circuit. This LC circuit is actually this resonator, microwave resonator. So this, and when you cover everything up, that looks like that from outside. Now we have actually started working with a little bigger quantum processor. That was 1 qubit to 5 qubit you started now. So these are different control, this is electronic control, how you control the qubit, or you implement the quantum gates. All these things are done through this device. So this is what is done. You have to do many kinds of quantum characterizations of this qubit. So qubit, as I mentioned, is a two-level system. Superposition between 0 and 1, we are working with that. But if you let it pass through a longer period, it undergoes oscillations between these two states. And that we can catch by measuring the probabilities, you see here. But you see that this amplitude is decreasing because quantum systems are very unstable. When it interacts with the environment, it goes out of its quantum length. So gradually it goes out of its quantum length. So how long it survives to offer you actual quantum behavior, that is also measured through this decay curve. So from here it's exponential decay. From that we can measure the T1 time, that means that's the effective time during which you can use it as a quantum system. But beyond that you cannot. So this is, now a few days back we have now changed this from 1 qubit system. We put a 5 qubit chip here, 1, 2, 3, 4, 5, 1 qubit, and these resonators are now two-dimensional. It's not boxes, because if you have to work with many, then the boxes you cannot fit in there. It takes too much space. In 2 dimension also you can design this easy structure that behaves much like the box. So those are here. This we have just put that in. Still everything, all connections are not complete. That we have to do. But you see these things are new. These are filters, different kinds of filters. And the temperature there is of course 10 millikelvin on this last plate. And these are all attached to 10 millikelvin temperature. So to conclude, a superconducting electric circuit can show quantum behavior, what I have shown. And such quantum circuits are used to make superconducting the qubits, it should be. That was what? Superconducting qubits and superconducting quantum computers. And I have mentioned some of the applications that you can do with quantum computation. And those are beyond the classical limit you can reach. And the people who have been working here, it's my younger colleague who was a postdoc in my group, now assistant professor, Nehal Mandal, and the 2 PhD students here. So with that, I thank you for listening. It is a little bit warm, but it's too sweet.
Okay,
So without sugar.
চিনি ছাড়া